All right, good morning. Good morning, everybody. Welcome on in. So we're moving ahead with things. We're sort of starting today the last two big topics of the course, and then basically we'll be done, and there'll be a couple days where I can talk about the project, and I can help you with the project and give you some ideas. At least I suspect we'll have a couple days for that, and then we'll go. So I'll talk about confidence intervals. Probably that will take us up to Thanksgiving. And then when we come back from Thanksgiving, we'll talk about hypothesis tests, talk about the project, talk about the project a little bit, and then semester's over. It's going to come very, very quickly. Let me make a note of something. So, and both of the ideas that we have left to talk about, confidence intervals and hypothesis tests, very important ideas, very important concepts. They absolutely should be, you should be representing those ideas in your project so that I can see what's going on and that you've applied them to multiple questions and, that you really have an idea of how to use these things, and I can see you using them correctly and go, okay, yes, this person understands what's going on here. So I've been kind of building up to this idea for a while. So some of the things I'm going to say in the next couple of weeks are going to sound familiar. Like, yeah, that's a phrase he said before. He keeps saying this phrase. But we're sort of filling in the gaps a little bit. We're filling in the whole concept of a confidence interval, and in a couple of weeks, the whole concept of a hypothesis test. But these ideas are weird, and they take a little bit of logic that I would say is beyond the level of logic that you've probably run across so far in everyday life or your math classes or stuff like that. It takes a little bit more understanding of really, really drilling down and focusing on the logic, right? A lot of times people just sort of let the logic drive themselves when they're having a conversation or trying to follow along. But this is one where you really need to pay attention to that logic. Otherwise, you're going to miss what's actually happening, especially in the hypothesis test, right? I find there the reasoning really throws people. They can go through and crunch the numbers, but really understanding those results can throw people a little bit. But that's important. That's what needs to come through in your project, is that you're interpreting your hypothesis test, not just saying, I ran a hypothesis test, this was our p-value, and here's what we did. You need to interpret those results. Tell me what they mean in terms of your questions, what they mean in terms of, students taking units and hours worked, or whatever it is that your concept is about. Give me that understanding of what the hypothesis test means relating to your topic. That's where you're actually doing statistics. That's where you're getting your A's and your B's on the project. Those kind of grades is when you've really thrown that kind of stuff in there. Otherwise, there's not a lot of points given for just going through the motions and saying, yeah, I did a hypothesis test. Here was our outcome, and so we did this. Explain to me, why do I care that you did a hypothesis test? Show me that you understand what it means, right, going forward. Okay, so our formal formulation of confidence intervals, right? And I've used this example a little bit before, but and it was to get you comfortable with it so you could start to see it coming together now. We have something on campus that we want to measure. Let's come up with something new that I've talked many times about the real situation that we did where we wanted to know what students think of the smoking ban. Let's just take, for instance, the vaccine mandate. Okay, and we're not going to get political with this. We're just sort of going to use it as an example for how to do things. We could ask the question, and some of you, I don't remember if it was this class, but I know people have asked questions about vaccines in the surveys that I'm giving to my different statistics classes. Let's just say you wanted to know what percentage of students support a vaccine mandate. Okay, so we send each of you out, and it's hard during a pandemic to sample people well, but let's just say we had a good way of sampling students on campus. Let's just pretend that we could randomly pick students' 900 numbers, and those students would actually respond to, say, an email so that you could get all of your data back, right? So that's sort of in a perfect world, but that's the first half of the class where we were talking about, well, how do you run a sample, and how do you survey people, and how do you do all that? That's chapters back. So let's just live in this hypothetical situation where we were able to make that work. Okay, we were able to conduct a survey. Each of you was able to conduct a survey, and it was done properly, and we could trust the data. Okay, and let's just say that the percentage of, I'm making this up, I literally have no idea what these numbers are because I haven't seen them, but I'll just make them up. Let's just say that 70% of students support a vaccine mandate, okay? Excuse me. So 70% of students supporting a vaccine mandate, that would mean that the true proportion of the population of Ventura College students who support a vaccine mandate is 0.7, right? 0.7 as a proportion correlates to about 70% of the population, okay? But we'll never know that. We'll never know if that's true. Like, there's no way to, the only way to perfectly figure out that it's 0.7 would be if we could ask to run a census. We could ask every single Ventura College student. Every single Ventura College student actually responds and responds honestly, right? That's a pretty big ask, not likely to happen. So what we do is we sample and we send each of you out. You ask 100 people, do you support the vaccine mandate? Yes or no? And you each come back. And you're all going to have values that are somewhere in the neighborhood of 0.7, right? Some of you might hit 0.7 exactly. Some people might be at 0.72, 0.68. You're going to see a few values that stray further away. You might even get like a 0.55 or something. Who knows? You're going to get some outliers, but you're going to see the results if we went around the room and asked everyone, what was your proportion? What was your proportion? What was your proportion? We'd see them piling up around 0.7, right? If we were to graph it on a graph, we'd see them piling up around 0.7. But before we even do that, let's just say you're sitting in the room and you've brought in your results, and I say, okay, somebody give me an estimate for what they think the true proportion of students who support the vaccine mandate is. And I put you on the spot and say, what do you think it is? Well, what are you going to do? You're going to give me the value that you measured as your proportion. Now, you might have measured 0.72 because that was the proportion for your sample. Now, notice how there's a difference between the 0.70, which is our, like, say we magically know the answer. That 0.70 is unknowable to us. All we know is that you got 0.72 when you measured it. So that's our best guess at what the proportion is. This is what we call the point estimate. Okay, the point estimate is a single value or point used to approximate a population parameter. So that's the best information you have. You go, well, when I conducted my sample, I got 72% or 0.72 as a proportion. We go, okay, well, that sounds good. We could go with that. And then someone behind you says, but I got 0.74. Oh, you got 0.74. Okay, well, they're close together, but you measured a little bit higher. And then someone says, but I got 0.68. That's my point estimate. That's what I got. That's what I think, that I trust my data before I trust your data. So maybe I think it's 0.68. So see how everyone in the room has a little bit different idea of what that true proportion is? And we'll never know. Like I say, it's a fantasy to think that we could know that true proportion. If we could know the true proportion, we wouldn't need statistics. We would just know it. We would just know the value. Instead, we have a bunch of people in the room who are all kind of in the same neighborhood. They're all these values are kind of around 0.7, but no one can really decide the right value, right? That, the quote unquote, the right value. So, so there's some disagreement. Well, I think it's 0.71. Well, I think it's 0.69, and I think it's 0.77 because that's what I got when I measured my sample, right? So the thing that this shows us is that most people in the room are wrong, right? There might be a few people in the room that got 0.70 as their proportion, but all the people who got 0.71 or 0.69 or 0.68 or 0.74, all those people are wrong. They came up with a good point estimate. They're in the neighborhood of being correct, but to just give a point and say, I think it's this, 90% of people in the room, maybe more, are wrong. Probably 95% of the people in the room would be wrong because you're picking a single point and saying, I think this is the answer. but it isn't, right? Because you can't all be right. You all have a range like that. It would form a normal graph, and most people would be incorrect. So a point estimate is a good way of targeting in the point estimate. Well, here, I'm trying to say three things at once. The sample proportion p hat is the best point estimate of the population proportion p. That's just a formal way of saying what I said a second ago, which is you're using the sample proportion that you measured as your best estimate for the true proportion. That's all that sentence is saying, right? If someone put you on the spot, you'd go, I don't know the true proportion, but I measured 0.71. Okay, that's your point estimate. That's what that means. So that gives us a good idea, a good target, but it's probably wrong, right? It's probably off by a little bit. So then what we do is we say, well, I think my point estimate is approximately in the right area. So what if instead of giving a point, I give an interval? And I say, I'm pretty sure the true proportion is within this interval of values. That's better than, imagine like throwing darts at a dartboard. When you throw a dart at a dartboard, right where that needle hits, that's got to be the exact spot that you needed to hit, right? But imagine if you could throw a dart and then it put a circle around it, and anything in that circle would count, right? Well, that's kind of what we're doing. We're taking the point, we're hitting an exact point, and then we're putting an interval around that point and saying, I think the proportion's probably in there somewhere. So instead of trying to pin it down to an exact value, we're saying there's a good chance it's in this interval. That's what we're trying to do here. So believe me, I don't like reading out of the textbook any more than you do, but sometimes they sum up stuff really well. So let's just say, in example 1, I kind of made up my own example, but we saw that 0.70 was our best point estimate of the population proportion P. That's in the example we just talked about. Someone would measure 0.70 and they'd go with that. But we have no indication of just how good our best estimate is. Part of the giveaway of that is that there's 40 of you sitting in a room and you all have slightly different answers, right? Imagine being in an algebra class where one person gets x equals 2 and some person gets x equals 2.1 and someone has x equals 2.05. Well, it's clear in that case there's a whole bunch of people with wrong answers. It's the same thing here statistically. You all measured a thing and almost all of you are going to be off by a little bit. Now, that doesn't mean the work you did is junk and we should throw it away. What it means is we're not magic here. We can't know the unknowable, but we can estimate the unknowable, right? That's what we're trying to do with statistics, is to estimate those unknowable values. Because a good point estimate has the serious flaw of not revealing anything about how good it is, statisticians have cleverly developed another type of estimate. This estimate, called a confidence interval, consists of a range or interval of values instead of just a single value. Okay, so we take that point that you got, we put an interval around it and say it's pretty likely that we have things in the true proportion falls inside of this interval right here. Okay. A confidence interval is associated with a confidence level, such as 0.95, which we would call a 95% confidence interval. The confidence level gives us the success rate of the procedure used to construct the confidence interval. The confidence level is often expressed as the probability or area, where alpha is the complement of the confidence level. That we can get into. You'll see that when you're doing the videos. So, what does that mean? Because sometimes people get a little sloppy with the wording that we use, and you don't want to do that. You want to be careful. So when you're doing the homework, watch how they give the conclusion for a confidence interval. Watch how they interpret it. A lot of students say, well, I'm just going to say it this other way, but the way they end up saying it is mathematically wrong, right? So we don't want to do that. Like, of course, you want to be able to say things in different ways, but sometimes when we're talking about things that are exact in science and statistics and mathematics, when you change the wording of something, the changing might seem insignificant to you, but it could be that you're changing the meaning in ways that you don't understand, and then what you're saying is just incorrect. And, I know in math classes, believe me, as a professor, I know as much as anybody that there is sometimes in certain math classes, there's this idea where it's like, oh, he's making me use this specific language. Why are math teachers so specific about language and I have to say it a certain way? And it's because as the student, you're not familiar enough with the mathematics to realize that the way you're saying it is just plain wrong, right? It's not that I don't like the vocabulary you're using. It's that when you're changing it around, you're not seeing that you're introducing flaws into the conclusion, into the statement. That's why we don't like it. I mean, in general, what do I care what words somebody uses as long as they're correct? Or if you change it into a wording that is incorrect, then I have to call you on it and say, that's not actually how that works. And you'd be surprised how often this happens in a math class where people will say, well, you said this thing and that's the same as this. Nope, they're not logically equivalent. So, you got to work on those logic and critical reasoning skills a little bit to be able to change that statement into something else and still have it mean the same thing. So what they're saying here with the confidence level, a lot of times people go, okay, we're 95% confident. Well, what does that mean? What does it mean to be 95% confident of something? It's not really clear, like from a definition, what that means. So when we do things mathematically and statistically, we're pinning them down. They mean something specific. So what is this confidence level? Let's read this part again. Where was it? A confidence level, a confidence interval is associated with a confidence level. The common three are 90%, 95%, 99%. Almost never you probably won't use a 90% confidence interval very much. Most books use the default of a 95% confidence interval, and that's a pretty good rule of thumb. If you are just going, you're just going to do a confidence interval, start with a 95% confidence interval. Now, you might change to something different. You might decide we really need a 99% confidence interval here. So that, because you might say, well, why don't we just do a 100% confidence interval? Well, I'll explain that in just a second. There's a price to pay. The more confident you are, the less exact you are, right? So it's kind of like in physics, right? These ideas of like quantum mechanics. The better you know the position of a particle, the less you know about its velocity. And those two things interchange. The more you know about its velocity, the less you know about its position. It's kind of the same thing here. The more confident we are in our confidence interval, the less helpful that interval is going to be, mainly because it grows. Okay, so I'll get to that in just a second. So what I want to talk about is, what does the 95% confidence interval mean? It doesn't mean we're 95% confident, because what does that mean? I don't know what that means from a technical standpoint. What it means here when we say a 95% confidence interval, that means that if we kept repeating this research where we conduct a survey, we get our point estimate, and around that point estimate, we construct a confidence interval, 95% of the time, that interval will contain the true proportion. Okay? Because that's what we're trying to do. We're trying to come up with an interval that I can say, I think the proportion's inside of this interval. Well, 95% confidence interval means we're successful 95% of the time. Now, again, you never get to know. You don't get to look in the back of the book in real life and figure out if your answer's right or not. So effectively what this means is, if we took 20 people and had them conduct surveys and do 95% confidence intervals, 19 of those people we would expect to be correct, and one of those people would have an interval where the proportion did not fall inside their interval. So that's what that means. 19 out of 20 is 95%. That's what we would expect, right? Is that 95% of the time, your confidence interval actually contains the proportion. 5% of the time, it won't. And again, I've repeated this, but it's bizarre. It's kind of weird the way people treat probabilities, because I guess we're maybe not teaching it well in this country. People don't understand probabilities that much. They think a 95% probability is the same as a 100% probability. No. 95% confidence or 95% probability means something will happen 95 out of 100. That means it won't happen 5 times out of 100, right? Right? People kept saying all the predictions were wrong when Trump beat Hillary Clinton. Hillary Clinton had a 80% chance of winning. That means Donald Trump had a 20% chance of winning. That means you run that election 100 times, Trump wins 20 times. Okay, so just because something is unlikely doesn't mean it will never happen. It just means it happens a lot less. So just be careful with the way you talk about the confidence intervals, because, and the level of that confidence interval, because the wording, if you say I'm 95% confident, you've just taken it from a scientific thing to something that doesn't really have a meaning. I don't know what you mean when you say you're 95% confident. Can you explain that to me in mathematical terms, what it means to be 95% confident? And, usually the person's going to go, well, I have a feeling. I have well, feelings are not, at least in this context, feelings are not mathematically being measured in this statistical way. We can measure a 95% confidence interval and see that it's mathematically understood to be right 95% of the time. Okay. So, why don't we just go with a 99% confidence interval? Why don't we just go with a 100% confidence interval? Well, what would a 100% confidence interval look like for, say, our example of students supporting the vaccine mandate? Well, here's an example. I am 100% sure that the percentage of students who support a vaccine mandate is somewhere between 0 and 100. Not helpful, right? Not helpful at all. I'm 100% sure of it. I'm 100% sure that the percentage of students who support a vaccine mandate is between 0 and 100. But it's not really helpful, is it? You're like, what? If I said that in a meeting, people would be like, why are you wasting our time? Because it's not helpful. It doesn't help us pin anything down. So 100% confidence interval is so wide as to be useless. When we start talking about 99% confidence intervals, 95% confidence intervals, those intervals are going to shrink down. So that's the price that we pay. We are sacrificing some certainty for usability. Okay, because if you think about it, it's necessary. If you want to impose more confidence on your confidence interval, that interval has to get bigger, because that's how the probability of your P being in the interval increases, is by increasing the interval. If we shrink the interval, it's less likely that the probability is in there. If we grow the interval, it is more likely that the proportion is in there. So that's the price you pay. Oh, I want to be really confident. Well, then that interval is going to grow. Now, so when would you pick a 99% confidence interval over a 95? Well, maybe lives are on the line, or it's amounts of money that just is very, very important or something, then, you might. I would rather have the airline industry using, when they're designing the next Airbus or whatever, I would rather have them using 99% confidence intervals on their safety procedures than a 95% confidence interval, right? So that's what you have to realize is, what is the consequences of what we're doing? The consequences of, say, a vaccine mandate being supported by the students, it's important, but it's not the only factor. As far as the opinions of the students. I mean, a lot of this was driven by safety and so on. So one input would be what the students think of it, but there's also a lot of medical and science being considered at the same time. But if we're off by the student opinion, so again, don't think of the overall picture of vaccines, because whether you get the vaccine or not obviously can have deadly consequences. But if we mismeasure the favorability of it by students, that's not going to cost anybody their lives. Right? If the true proportion of students who support a vaccine mandate is 0.7 and we measure it to be 0.65, no one's going to die. Okay? So in that case, we'd go, yeah, probably reasonable to use a 95% confidence interval. If you're working for Boeing and you're trying to come up with the true proportion of times that your safety feature is going to fail in flight, you better be pretty confident about that, because that's going to inform how you design the rest of the plane, right? How many of those safety procedures get redundancies put into place for when they fail. It's going to be based on that true proportion. So you better be pretty sure, because you don't want to be responsible for an entire plane of people dying, right? So that's kind of the measurement. But again, that 95% confidence interval is going to grow, and it's going to, we like answers, and that's what the hypothesis test is going to be. We like when we ask an answer and we ask a question and we get one answer, right? But a lot of times in real life, especially in statistics, you can't just get one answer because the answer isn't really known. So it's satisfying to get one answer, but you're sacrificing accuracy. It could be that the answer you're getting is incorrect. If we get an interval, that's not as satisfying to tell someone, well, we're pretty sure the proportion of students who support a vaccine mandate is somewhere between 0.67 and 0.73. It's somewhere in there. That's not very satisfying. We want a number, right? We want an answer. I want to know for sure what it is. But in order to force that exact answer, you're probably giving up the fact that you're probably wrong, right? Whereas if we give an interval, we're probably a lot more sure that it lies in there. That's the whole idea behind these. Okay, interpreting a confidence interval. So this is important. This is an important idea, right? So there's the correct and incorrect way. In fact, there's numerous incorrect ways. Students find many new ways of incorrectly stating a confidence interval. It's important that you state it correctly. This is a thing I look for because I keep telling you that it's important that I have your interpretations and your conclusions in your project. Well, if your conclusions are stating things incorrectly, that's not good, right? Your conclusions need to be stated in the way that is correct. And then I go, oh, this person knows what they're talking about. They really learned statistics. So let's take, for example, we must be careful to interpret confidence intervals correctly. There is a correct interpretation and many different and creative incorrect interpretations of the confidence interval. And this is what I was kind of alluding to earlier. It's easy for students to read this and go, I'm just going to say it this different way, right? And we encourage you to do that in like an English class. You're not supposed to just read something and then copy it down word for word into your essay. You're supposed to restate it in some kind of a way that is your own. The danger with doing that statistics, especially at this level where you're brand new to the idea, is that your interpretation is probably wrong. It's probably an incorrect interpretation. So you want to be careful about rewording things. Other than just, insert your noun and your verb that have to do with your problem. So here's a correct way of stating it. We are 95% confident that the interval from 0.677 to 0.723 actually does contain the true value of the population proportion P, right? So remember I kind of said, well, what does that mean to be 95% confident? So then they go on to state. This means that if we were to select many different samples of size 1,501 and construct the corresponding confidence intervals, 95% of them would actually contain the value of the population proportion P, right? Note that in this correct interpretation, the level of 95% refers to the success rate of the process being used to estimate the proportion. So a lot of times students will say, oh, I'm 95% confident, and they have no idea what that means. They think of it as, well, I have a feeling in my gut that I'm pretty sure, but I'm not 100% sure, so that's 95% confident. That's not what that means. You want to be kind of thinking about this part. Like, this means that if we were to select many different samples and repeatedly conduct this experiment, 95% of the time they would contain the actual population proportion P. That's what it means to be 95% confident. So just be careful with your language. Okay, here is one of many incorrect ways of stating it. There is a 95% chance that the true value of P will fall between 0.677 and 0.723. It would also be incorrect to say that 95% of the sample proportions fall between 0.677 and 0.723. So right there's two different ways of stating it. That if someone said them and you weren't, if you're not real comfortable with statistics, you might go, yeah, I think that's maybe the same thing, but they're not. There is a difference there. So you have to be careful. And they even say here, caution, know the correct interpretation of a confidence interval is given above. So the way that it's stated here. Pretty important to say it correctly. That's kind of if you're giving interpretations that are wrong, that doesn't look good on a project. Okay, so it basically is like this. I don't remember if we talked about if that was the other class or this one where we showed this graph. So imagine 20 people in the room come up with a confidence interval. See this one person right there? Theirs doesn't contain the true proportion P. Theirs is outside of it. But these other 19 do. That's what you expect from a 95% confidence interval. 19 of the people will be correct. One person will be wrong. And you might go, yeah, but can't they see that the P is not in their interval and then they just fix it? No, because remember, we never get to know where this line is. This line is always unknown to us. It is always hidden. If it wasn't hidden, we wouldn't need to be doing confidence intervals, right? It's never really knowable. And I think that's the thing I see students get very confused about is they're waiting for the end where they go, okay, now tell me the answer to see if my confidence interval was right. And it's like, we never know the answer. That's the whole reason we're doing all of this work, right? It's not just so that you can drag your pen around on a piece of paper. It's because that's the only way we're going to come up with some idea of what this p-value is by running these confidence intervals, okay? Right. Okay. You won't have to get into a lot of this stuff because you're using StatCrunch, which is going to run the confidence intervals for you, which is great. Pretty straightforward to run a confidence interval in StatCrunch, so you don't need to do all these other tools that we're looking at. You do get a margin of error. So when we're talking about this error here, what does it mean? Well, remember how at the beginning of class we started with this example where the true proportion is 0.7, but all of you ended up with a measurement close to 0.7, 0.72, 0.68, stuff like that. Well, remember how I kept pointing out, well, most of you are wrong, but you're just wrong by a little bit, right? Well, that's an error. There's that measurement in between the true proportion, which we'll never know, and your value that's called an error, right? So when data from a simple random sample are used to estimate a population proportion P, the margin of error, denoted by capital E, is the maximum likely difference between the observed sample proportion P hat and the true value of the population proportion P. The margin of error E is also called the maximum error of the estimate and can be found by multiplying it. They get into stuff we don't need to know about because you're using StatCrunch to calculate these. But just be aware, there's always inherently some error in there. We're never getting, like, a lot of times when we're doing this in class, a student gets something on the calculator that has a lot of decimals to it, 0.74532951745. People go, man, that's so accurate. Like, probably not. It's probably off. It's very precise, but it's probably incorrect because you're probably close to the value, but not quite there, right? Think of it as a dartboard. You throw the dartboard and you don't quite hit the red bullseye. You hit that ring right outside the bullseye. Well, you were close to the bullseye, but also you didn't hit it, right? You weren't exactly in the right spot, okay? So our confidence interval, basically that E value, if you think about it, basically what we do is we calculate under certain conditions, and like I say, StatCrunch will do this for you, but we calculate this likely error value. What is the likely error value that most people are getting when we send them out to measure the proportion of students to support a vaccine mandate? Well, then what we do is we take that error and we use that around our point estimate to come up with our interval. Now, again, this is great because see all these fancy looking formulas? You don't have to worry about that because StatCrunch does it. But you should understand where this is coming from. We take your point estimate as the middle of the interval, and then we expand that interval left and right by the margin of error, this error value, this expected error value. So that tells us how wide to make the thing. That's why the more and more confident we are that error value grows, we need a bigger interval, right, to make sure that we're capturing those probabilities. So your p hat, that's your point estimate that you measured in your sample, and then E is this sort of, it's going to be a little bit invisible to us because you're not actually going to calculate them as much in here, but we move either direction from that point estimate enough to create an interval. That is our confidence interval. That is how that thing is created. So when StatCrunch does its magic and spits out a confidence interval to you, you'll at least know, oh, it took my point estimate, which is the proportion for the column in StatCrunch. It calculated that proportion for that sample, and then according to the level of confidence that I want, it decided how wide to make that interval, and it built that interval around my point estimate. So, you know, if most of you in the room had measurements like 0.72, 0.69, 0.68, 0.71, but you constructed an interval that went, you know, all your intervals are going to be shifted a little bit, but if most of them contain 0.70, then your confidence interval is correct. The true proportion, even though we'll never know it, the true proportion falls in that interval somewhere. That's what we're trying to do here, okay? We don't have to worry about this because you'll use technology to construct them. Right. So, and you can determine sample size. So one nice thing is you can, this is what you would do before you actually do your work. This is part of what you would do when you are designing your experiment from the early stages. You'd say, well, we want to be this accurate, and using that, you can use some formulas here, right, that are given in here, which we won't do too much with this, but you can come up with formulas that will tell you then how many people do you need to survey. So I keep just coming up with the magic number of 100 students surveyed. But maybe, you know, maybe that's not good enough for what we're trying to do. We can actually run this, and it would say, actually, you should be asking 327.5 students. Well, what does that mean? What is 327.5 students? Well, how do you round that? You would always round up, because if you round down, then your percentages are slightly smaller than they need to be. So if you round up on your end, then you go, okay, I'm actually supposed to go ask 328 students what their opinion is, and then you could go do that. And then you know you're going to end up with an exact enough confidence interval in the end. All right? How are we on time? There's a weird thing that happens here. Let's say someone gives you a confidence interval, but you didn't know the proportion that they calculated. So maybe someone did some research and you're getting it late. Now you're being brought into the project, but you wanted to know that proportion that they found in the sample, but you can't find it anywhere. Well, you can get it from the confidence interval. It's the middle, right? It's the middle of your confidence interval is that point estimate. So you can get it that way. Here's the problem that I see is a lot of students take a confidence interval and they say, well, the true proportion must be right in the middle, right? No. If we knew what the true proportion is, why would we have constructed a confidence interval? The proportion in the middle of your interval is the sample proportion that you found when you were measuring things. That doesn't mean that it's the proportion for the entire population. Okay, so there's like a subtle difference there, but I see students go in this circle of they get a point estimate for the proportion, they create a confidence interval, they cut the confidence interval in half and say, now I know the proportion of the population. Well, you could have skipped that whole step by just calling it the proportion, the sample proportion in the first place, but that's not valid. That's not a valid thing to do. So be careful with that because it doesn't end well. There are different formulas for constructing confidence intervals, so you can do it a few different ways. For this class, you don't need to worry about that. We're just going to go with the way that StatCrunch is constructing your confidence intervals. If any of you go on to become statistics majors, then yeah, you're going to learn some different confidence intervals and you're going to learn different ways to do it. again, the good news is more and more statistics is being done by computers. So a little more attractive than it was, say, 20 years ago when you're getting into statistics and you're having to do a lot of crazy calculations, looking up tables and stuff. Now there's software that does that. And then the focus is, okay, how do you use the statistics? A lot more interesting. So let's see. So we just talked about confidence intervals for proportions. There's also confidence intervals for a mean. So remember, a proportion is like a percentage. You ask people a question, do you support a vaccine mandate? Their answer is either yes or no. And you want to know what percentage of those people support a vaccine mandate. That's the proportion. That's what a proportion is. The mean is different, right? The mean would be, say we run a bakery, and we make cupcakes, but our cupcakes are actually bought. We're actually large scale. Our cupcakes have caught on. They're very popular. So we're kind of we're increasing. We want to just sell to people when they come into the bakery. We actually have a factory spitting out these cupcakes, and we deliver them to Vaughn's and Trader Joe's and different places that are going to sell our cupcakes. Well, we need some quality control. So we want to know, what are the weights of the cupcakes? Like, are they varying? Are some cupcakes bigger than others? Like, how well are we making sure there's consistency from cupcake to cupcake? Okay. So you might want to know the mean. What is the mean weight of the cupcakes that are coming off the line? Because then when we measure one, we can see how far it is from the mean. Well, how would you estimate that population mean? Well, we could come up with a confidence interval. So it's the same idea as the proportion, where we have an interval and we say, we think the true unknowable proportion lies somewhere in this interval. We can do that with the mean and say, we think the true mean, which is unknowable, lies somewhere inside of this interval. Okay. Now, books sometimes present two ways of doing this. This is where sigma is known and where sigma is not known. This way, where sigma is known, they have good mathematics for doing it that way, but you almost never see that in real life. Like, just think about that. How would you know? You would know the standard deviation, but you wouldn't know the mean? That seems pretty weird. So you don't usually do it that way. So then you actually end up doing it the way it's given in this other section. Where you have a distribution where sigma is not known. That's how it's generally going to be. So the mean that you measure from your sample is your best point estimate, just like before. If you think about it, that's probably the only piece of information you have at the beginning. That's your best bet to move forward and do things. Okay. Degrees of freedom, you shouldn't have to worry about very much because StatCrunch is sort of handling all that. You should just know the degrees of freedom is whatever your n is minus 1. So remember, lowercase n is always your sample size. Subtract 1 from that, you get the degrees of freedom. So if someone brings it up, you'll know what it is, but you don't really have to worry about it too much. We use this thing called the student T distribution. StatCrunch is going to do it for you. You don't have to worry about that, but sometimes there's a little bit of confusion, so I just want to explain something. The fact that it's called student T distribution leads students to think, oh, this is just something we're doing in stats class, but it's not like a real thing out in the world. The reason it's called student is not because students use it. It's because the person who created this table and this concept for this particular idea for how to do this, basically this person figured out how to do this using statistics, was working for the Guinness Company. He was doing quality control for the Guinness Brewery back in the day. Well, most companies don't want their employees publishing papers because the company wants, they want to keep it's like trade secrets, right? Anything you have that is usable, you can try to use to leverage more profit from other people. So they didn't want this being published. So he had to, this person, I forget the name of this individual, William Gossett, said, no, this is important that the world sees how to do the statistics. So he published the information under the name student. He just called it student and then published the work. That way it wasn't traced back to him and he didn't get fired. I don't think he got fired. So when we talk about a student T distribution, it's just a name because of, intellectual property rights dating all the way back. I don't know what year it was, 150 years ago or something, 170 years ago, or well, I guess it probably published it about 150 years ago. It's probably right about at the beginning. Companies just more concerned about profit than sort of helping the world become a better place, trying to keep all this stuff secret. But he got that stuff out there. So even that long ago, intellectual property discussions were holding back science and medicine and understanding and stuff like that. So luckily, he went ahead and published that work. But it's just called the student distribution. So don't let that confuse you. It's not something that we give to students. It's something that we give to everybody who's doing this kind of thing. So you can see this looks familiar, right? What do you do? Your X bar, your sample mean, is the center point for your interval. So you should see that when you're seeing what StatCrunch spits out to you, go, oh yeah, I can see how they built this interval around the mean that was the measurement for my sample, right? Don't let it be like a magic box. You're not going to understand anything if you blindly look at the numbers coming out of StatCrunch and go, okay, you want to understand them a little bit. So we take the mean that you measured, your proportion mean, or your sample mean, and then we extend it by a certain amount that is calculated by the computer. That part you don't have to worry too much about. That gets kind of just a fancy formula. We create an interval, and then we're pretty sure the true mean falls somewhere in there. Right? So then we could say, okay, we think the true mean weight of our cupcakes coming off the assembly line is between 47.4 and 48.3 grams, or whatever it's going to be. We can make that argument. Right. And I think that's about it for where we're going for today. We'll do some examples next time, talk a little bit more about confidence intervals, but you'll see the details, right? I'm usually trying to give the overall picture because that's where students get stuck. Students can go in and copy the buttons being pushed in the homework. It's being able to understand what it means, which is where the real knowledge of this class lies. Making sense of it all. So that's kind of what we're talking about. We will continue this discussion with confidence intervals next time. Anybody who wants to talk to me in Zoom, please hop in there and I will help you out with whatever you have concerns about. Okay, thanks everybody. I will see you. Let's see, today's Wednesday. I'll see you on